Ever wondered how data packets know exactly where to go in a vast network? Or perhaps how OSPF, the backbone of many enterprise networks, works? Just like a well-trained postman who knows every nook and cranny of his route, these little packets of information have their own unique way of finding their destinations. And OSPF? It's like the grandmaster of network routes, a true marvel in the world of networking. Well, you're in for a treat as we unravel these networking concepts in this episode. To understand the magic of data packet delivery, we must dive into IP routing. Imagine being a postman in a sprawling city where each building represents a network, and each apartment in the building symbolizes a specific device on the network. Your job is to deliver letters, or in our case, data packets to the correct address. This is the essence of IP routing. IP routing is the process that allows data to travel across multiple networks. It's like a GPS system for data packets, guiding them to their destination through the vast, interconnected web of networks that make up the internet. In the center of this process is the router, the traffic director of the cyber world. Routers maintain a complex map of the internet known as the routing table. This table is a database that stores information about different paths data packets can take to reach their destination. A routing table is a bit like a city map, but instead of streets and buildings, it contains routes and networks. It's filled with entries, each representing a different network. An entry typically contains three crucial pieces of information: the network destination, the next hop, and the metric. The network destination is the final stop of the data packet, the address on the letter, if you will. The next hop is the direction the packet should take from the current router to continue its journey. Finally, the metric is a value that represents the cost of a route. The lower the cost, the better the path. Routers use this table to determine the best path for forwarding packets. When a data packet arrives, the router scans the table, comparing the packet's destination with the network destinations in the entries. Once it finds a match, it uses the corresponding next hop and metric to forward the packet towards its final destination. By now, you should have a clearer picture of how IP routing works. It's a fascinating process, isn't it? But it doesn't stop there. In the world of IP routing, there are protocols that make the process even more efficient, and one of the most powerful amongst them is OSPF. Now that we've demystified IP routing, it's time to delve into one of its most powerful protocols, OSPF. OSPF, or Open Shortest Path First, is a key player in the world of IP routing. It's a high-level protocol used within an autonomous system like an enterprise network. But what makes OSPF special? And why is it so widely used? Let's delve into it. OSPF is a link state routing protocol. This means it maintains a map of the entire network called the link state database. This database is shared among all the routers within the same hierarchical area. This comprehensive view of the network allows OSPF to calculate the shortest path between any two nodes using a method known as Dijkstra's algorithm. One of the reasons OSPF is so widely adopted is because of its scalability. OSPF divides larger networks into smaller, more manageable segments known as areas. This division reduces routing overhead, speeds up convergence, and makes the network easier to manage. Another key feature of OSPF is its support for both IPv4 and IPv6, making it a versatile choice in the world of network routing. OSPF also has built-in mechanisms for authentication, providing an extra layer of security. But perhaps the most compelling feature of OSPF is its dynamic nature. OSPF routers continuously send out hello packets to their neighbors. These packets serve as a heartbeat, allowing routers to know if a neighboring router is up or down. If a router fails or a link goes down, OSPF can quickly recalculate routes and adjust accordingly. This ability to rapidly adapt to changing network conditions makes OSPF an exceptionally robust and reliable routing protocol. OSPF is also an open standard, which means it's not tied to any one vendor. This gives network engineers the flexibility to use routers from different manufacturers while still ensuring compatibility and interoperability. In summary, OSPF's efficiency, versatility, and dynamic nature make it a preferred choice for many network engineers. It's a powerful tool in the IP routing toolbox, helping to keep our networks connected and our data flowing smoothly. But how does OSPF work? Let's find out. OSPF has a unique way of determining the best path for data packets. Let's dive into the magic behind it. At the heart of OSPF lies a clever algorithm called the Dijkstra's algorithm. This algorithm, named after its creator, Edsger Dijkstra, is used to calculate the shortest path for data packets to travel from one network node to another. Imagine our network as a city, and our data packets are like travelers trying to navigate through it. The Dijkstra's algorithm acts like a GPS system, finding the shortest, fastest route to the destination. It calculates the total cost of each path, which is determined by the bandwidth of the links along the path. The path with the lowest total cost is considered the shortest path. But what happens when there's a change in the network topology, such as a link failure or a new link being added? OSPF handles this quite efficiently. When a change occurs, the affected router sends out link state advertisements or LSAs to all other routers in the network. These LSAs contain information about the change, allowing all routers to update their routing tables with the new network topology. Once the routers receive the LSAs, they run the Dijkstra's algorithm again to recalculate the shortest paths. This ensures that data packets are always traveling along the most efficient routes, even when there are changes in the network. OSPF's robustness doesn't stop there. It also divides large networks into smaller areas to improve efficiency and reduce routing table size. Each area runs its own instance of OSPF, and routers within the same area share the same link state database. This hierarchical design greatly simplifies the management of large networks and enhances their performance. So OSPF is not just about finding the shortest path. It's about constantly adapting to changes, efficiently handling large networks, and ensuring that data packets always find their way, no matter what obstacles they encounter. OSPF's dynamic nature is indeed fascinating, isn't it? Now, how about we get our hands dirty with some OSPF2 configuration? Configuring OSPF2 is like setting up the pieces on a chessboard. It's all about strategic placement and knowing how each piece, or in our case, each router, plays its part. First things first, we'll need to enter the global configuration mode on our router. We do this by typing configure terminal, or conft for short. This is where we roll up our sleeves and begin the real work. Next step, we enable the OSPF process. We do this by typing router OSPF followed by a process ID of our choice. This ID is locally significant, meaning it only matters to the router we're configuring and doesn't affect the OSPF operations. Now, we need to define the network that OSPF will run on. We use the network command followed by the IP address, wildcard mask, and area ID. The wildcard mask is the inverse of a subnet mask, and the area ID is where we place the network within our OSPF topology. Once we've done that, we're halfway there. We've got our OSPF running, but we need to ensure it's optimized for our network. That's where OSPF cost comes in. It determines the best path for data to travel. We can manually set this cost using the IP OSPF cost command followed by a value. Finally, we need to ensure that OSPF is running smoothly. We do this by checking the OSPF neighbor table. This table lists all the routers OSPF is communicating with. We can view it by typing show IP OSPF neighbor, and voila, we've configured OSPF2. But remember, this is just one part of the puzzle. OSPF is a dynamic protocol that adapts to network changes. So, it's crucial to keep monitoring and tweaking as necessary. That wasn't too hard, was it? But practice makes perfect. So, go on, dive into the world of OSPF v2, play around with the commands and see the magic unfold. We've covered quite a bit of ground today, haven't we? Indeed, We've journeyed through the fascinating world of IP routing and the Open Shortest Path First Protocol, better known as OSPF. We started our exploration by unpacking the components of the routing table, a vital tool used by routers to decide where to send packets. We learned how this table contains information about directly connected networks, remote networks, and how routers use this data to determine the best path for data transmission. From there, we delved into the world of OSPF, a link state routing protocol that's a favorite among network engineers. We discovered how OSPF routes packets within a single autonomous system and how it uses a hierarchical network design. We also learned about the process of OSPF operation, including the formation of neighbor relationships, the exchange of routing information, and the computation of the shortest path using Dijkstra's algorithm. We then rolled up our sleeves and got our hands dirty with the configuration of single area OSPF v2. We walked through the steps of configuring OSPF v2, from enabling OSPF on a router, setting the router ID, to defining the OSPF area and network. In the end, whether you're a seasoned network engineer or just starting out, the world of IP routing and OSPF offers a wealth of knowledge to explore and master. With this, we conclude our episode on IP routing and OSPF. Keep exploring, keep learning.